Welcome to the fascinating world of coordination compounds. These unique chemical structures play a vital role in both nature and industry. Coordination compounds, also known as complex compounds, consist of a central metal atom or ion surrounded by molecules or ions called ligands. Their study not only deepens our understanding of chemistry, but also opens doors to innovations in medicine, materials science, and environmental technology. In this video, we'll explore what makes coordination compounds so special, how they're formed, and why they matter. Let's embark on this journey to uncover the secrets behind these chemical marvels. Coordination compounds are chemical entities formed when a central metal atom or ion binds to surrounding molecules or ions known as ligands. These ligands donate electron pairs to the metal, creating coordinate covalent bonds. The resulting structure is called a coordination complex. This concept is fundamental to understanding how metals interact with other substances, influencing everything from biological systems to industrial processes. By grasping the basics of coordination compounds, we set the stage for exploring their diverse applications and intriguing properties. At the heart of every coordination compound lies a central metal atom or ion. This metal acts as the anchor, attracting ligands through its positive charge and ability to accept electron pairs. Common metals found in coordination compounds include transition metals like iron, copper, and cobalt. The nature of the central metal greatly influences the properties and stability of the resulting complex. Understanding the role of the central metal is crucial for predicting how coordination compounds behave in different environments. Ligands are molecules or ions that surround and bind to the central metal atom in a coordination compound. They act as electron pair donors, forming coordinate covalent bonds with the metal. Ligands can be simple ions like chloride or more complex molecules such as ammonia or ethylenediamine. The type, number, and arrangement of ligands around the metal determine the geometry and reactivity of the coordination compound. Ligands are essential for the stability and function of these complexes. Ligands come in various forms, each with unique characteristics. Monodentate ligands attach to the central metal through a single donor atom like water or chloride. Bidentate ligands use two donor atoms to bind, such as ethylenediamine. There are also polydentate ligands, which can attach at multiple points, forming more stable complexes. The diversity of ligands allows for a wide range of coordination compounds with different properties and application. Coordination number refers to the number of ligand donor atoms directly bonded to the central metal atom in a coordination compound. This number can vary, typically ranging from 2 to 8, depending on the size and electronic structure of the metal and ligands. For example, in Fe(CN)64, the coordination number is 6, as 6 cyanide ions surround the iron center. Understanding coordination numbers helps predict the geometry and stability of complexes. Coordination compounds can adopt various geometric shapes based on their coordination number and the nature of the ligands. The most common geometries include octahedral, tetrahedral, and square planar. For instance, a coordination number of 6 often leads to an octahedral geometry, while 4 can result in either tetrahedral or square planar arrangements. The geometry influences the compound's chemical behavior and physical properties, making it a key aspect of coordination chemistry. Coordination compounds follow specific rules set by IUPAC. The ligands are named first in alphabetical order, followed by the central metal. If the complex is an anion, the metal's name ends with 8. Prefixes like D, tri, and tetra indicate the number of each type of ligand. For example, CoNH3, 6Cl3 is called hexamine cobalt, Roman 3 chloride. Mastering nomenclature is essential for clear communication in chemistry. Isomerism occurs when coordination compounds have the same formula but different arrangements of atoms. There are two main types, structural isomerism and stereoisomerism. Structural isomers differ in how ligands are connected to the metal, while stereoisomers have the same connections but different spatial arrangements. This phenomenon adds complexity and diversity to coordination chemistry, influencing properties like color, reactivity, and biological activity. Structural isomerism in coordination compounds arises when the connectivity of ligands to the central metal differs. Types include linkage isomerism, where a ligand can attach through different atoms, and coordination isomerism, involving the exchange of ligands between two metal centers. These variations can lead to compounds with distinct chemical and physical properties, even though their formulas are identical. Stereoisomerism occurs when coordination compounds have the same connections but differ in the spatial arrangement of ligands. This includes geometric isomerism, where ligands are positioned differently around the metal, and optical isomerism, where compounds are non-superimposable mirror images. Stereoisomers can have vastly different chemical behaviors, making this concept crucial in fields like pharmaceuticals and catalysis. Geometric isomerism is a type of stereoisomerism where ligands occupy different positions around the central metal. In square planar and octahedral complexes, ligands can be arranged cis, adjacent, or trans, opposite. For example, in PTNH3-2Cl2, the cis and trans forms have different chemical and biological properties. Recognizing geometric isomers is important for understanding the behavior of coordination compounds. Optical isomerism arises when coordination compounds exist as non-superimposable mirror images, known as enantiomers. These isomers rotate plane polarized light in opposite directions. Optical isomerism is common in octahedral complexes with bidentate ligands. This property is particularly significant in biological systems, where only one enantiomer may be biologically active. Understanding optical isomerism is key in drug design and synthesis. Bonding in coordination compounds involves coordinate covalent bonds, where ligands donate electron pairs to the central metal. This interaction is explained by theories such as valence bond theory and crystal field theory. These theories help us understand the electronic structure, color, magnetism, and reactivity of coordination complexes. By studying bonding, chemists can predict and manipulate the properties of these compounds for various applications. Valence bond theory explains the bonding and coordination compounds by considering the overlap of atomic orbitals. Ligands donate electron pairs into empty orbitals of the central metal, forming coordinate covalent bonds. This theory helps predict the geometry and magnetic properties of complexes. While useful, it has limitations in explaining color and some electronic behaviors, leading to the development of more advanced models. Crystal field theory provides a deeper understanding of coordination compounds by focusing on the interaction between the metals' d orbitals and the electric fields created by ligands. This theory explains the splitting of d orbital energy levels, which accounts for the color, magnetism, and stability of complexes. Crystal field theory is essential for interpreting the electronic structure and reactivity of transition metal complexes. Any coordination compounds are vividly colored due to electronic transitions within the metal's d orbitals. When light hits the compound, certain wavelengths are absorbed as electrons jump between split d orbital energy levels. The remaining light is reflected, giving the compound its characteristic color. This property is not only visually striking but also useful in analytical chemistry and material science. Magnetic behavior of coordination compounds depends on the arrangement of electrons in the metal's d orbitals. Compounds with unpaired electrons are paramagnetic and attracted to magnetic fields, while those with all paired electrons are diamagnetic and repelled. Crystal field theory helps predict these properties, which are important in designing magnetic materials and understanding biological systems. Stability of a coordination compound is influenced by factors such as the nature of the metal, the type of ligands, and the overall geometry. Chelating ligands, which form multiple bonds to the metal, often increase stability, a phenomenon known as the chelate effect. Understanding stability is crucial for applications in medicine, catalysis, and environmental chemistry. Chelating ligands are special because they can attach to the central metal at multiple points, forming ring-like structures. This multipoint attachment greatly enhances the stability of the coordination compound, a phenomenon called the chelate effect. Common chelating agents include EDTA and ethylene diamine. Chelating ligands are widely used in medicine to remove toxic metals from the body and in industry for water treatment. Coordination compounds have significant medical applications. For example, Cisplatin is a platinum-based coordination compound used as a chemotherapy drug to treat various cancers. Chelating agents are employed to treat heavy metal poisoning by binding and removing toxic metals from the body. The versatility of coordination chemistry continues to inspire new treatments and diagnostic tools in healthcare. Industry, coordination compounds are essential in processes like catalysis, electroplating, and pigment production. For instance, catalysts based on coordination complexes speed up chemical reactions in the manufacture of plastics and pharmaceuticals. Coordination compounds also play a role in water purification and metal extraction, showcasing their importance in modern technology. Coordination compounds are vital in biological systems. Hemoglobin, the oxygen-carrying molecule in blood, is a coordination complex of iron. Chlorophyll, responsible for photosynthesis in plants, contains a magnesium coordination center. These examples highlight how coordination chemistry is fundamental to life processes, enabling essential functions like oxygen transport and energy conversion. Coordination compounds contribute to environmental protection. Chelating agents are used to remove heavy metals from wastewater, preventing pollution. Some complexes act as sensors to detect environmental toxins. By harnessing the unique properties of coordination compounds, scientists develop innovative solutions for cleaner water and a healthier planet. Material science benefits greatly from coordination compounds. These complexes are used to create advanced materials with specific magnetic, optical, or electronic properties. For example, coordination polymers and metal-organic frameworks (MOFs) are designed for gas storage, separation, and catalysis. The versatility of coordination chemistry drives innovation in developing new materials for technology and industry. Coordination polymers and metal-organic frameworks (MOFs) are extended structures formed by linking metal centers with organic ligands. These materials have high surface areas and tunable properties, making them useful for gas storage, separation, and catalysis. MOFs in particular are at the forefront of research for clean energy and environmental applications. Coordination compounds are invaluable in analytical chemistry. They serve as indicators in titrations, help detect metal ions in solutions, and are used in colorimetric assays. Their ability to form colored complexes with specific ions allows for sensitive and selective analysis, making them essential tools in laboratories worldwide. You might be surprised to learn that coordination compounds are part of everyday life. From the colors in gemstones to the effectiveness of laundry detergents, these complexes are all around us. Even the blue pigment in Prussian blue paint is a coordination compound. Their presence in daily products highlights their practical importance beyond the laboratory. Study of coordination compounds dates back to the 19th century with Alfred Werner's pioneering work. Werner's coordination theory explained the structures and bonding of these compounds, earning him the Nobel Prize in Chemistry in 1913. His discoveries laid the foundation for modern coordination chemistry and continue to influence research today. Alfred Werner revolutionized chemistry by introducing the concept of coordination numbers and the spatial arrangement of ligands. His work explained the existence of isomers and the stability of complexes, which classical theories could not. Werner's insights remain central to our understanding of coordination compounds and their diverse behaviors. Today, research in coordination chemistry is vibrant and multidisciplinary. Scientists are designing new ligands and metal centers to create complexes with tailored properties for catalysis, medicine, and materials science. Advances in spectroscopy and computational chemistry allow for deeper insights into the structure and function of coordination compounds, driving innovation across scientific fields. Spectroscopic techniques such as UV-Vis, IR, and NMR spectroscopy are essential for studying coordination compounds. These methods reveal information about the electronic structure, bonding, and dynamics of complexes. Spectroscopy helps chemists identify unknown compounds, monitor reactions, and understand the behavior of coordination complexes in various environments. Computational chemistry uses computer simulations to model the structure and properties of coordination compounds. By applying quantum mechanics and molecular modeling, scientists can predict how complexes will behave, design new compounds, and optimize their functions. This approach accelerates discovery and innovation in coordination chemistry. Coordination compounds are at the heart of many catalytic processes. Homogeneous catalysts, such as those used in the production of polymers and pharmaceuticals, often rely on transition metal complexes. These catalysts increase reaction rates and selectivity, making chemical manufacturing more efficient and sustainable. Coordination compounds are used in environmental catalysis to remove pollutants and convert harmful substances into less toxic forms. For example, catalytic converters in cars use platinum-based complexes to reduce emissions. These applications demonstrate the power of coordination chemistry in addressing environmental challenges. Sensors based on coordination compounds can detect metal ions, gases, and biological molecules with high sensitivity. These sensors are used in medical diagnostics, environmental monitoring, and industrial safety. The ability to design complexes with specific recognition properties makes coordination chemistry a valuable tool in sensor technology. Photochemistry involves the interaction of coordination compounds with light. Some complexes can absorb light and undergo chemical changes, making them useful in solar energy conversion, imaging, and photodynamic therapy. Understanding the photochemistry of coordination compounds opens new possibilities for renewable energy and medical treatments. Nanotechnology leverages coordination compounds to create nanoscale materials with unique properties. These materials are used in drug delivery, imaging, and electronics. Coordination chemistry enables precise control over the size, shape, and function of nanomaterials, driving advances in medicine and technology. Throughout history, coordination compounds have contributed to art and culture. The vibrant colors of stained glass, ceramics, and pigments often result from metal complexes. Artists and craftsmen have harnessed the beauty of these compounds to create lasting works, demonstrating the intersection of science and creativity. Despite their versatility, coordination compounds present challenges. Synthesizing complexes with precise structures, understanding their reactivity, and predicting their behavior in complex environments require advanced techniques and interdisciplinary collaboration. Overcoming these challenges drives progress in chemistry and related fields. The future of coordination chemistry is bright, with ongoing research aimed at developing new materials, medicines, and technologies. Scientists are exploring sustainable synthesis methods, environmentally friendly catalysts, and smart materials that respond to external stimuli. Coordination compounds will continue to shape the future of science and technology. Let's recap the key concepts of coordination compounds. We've explored their structure, types of ligands, bonding theories, isomerism, and diverse applications. From medicine to materials science, coordination chemistry is a cornerstone of modern science. Understanding these compounds equips us to tackle challenges and innovate across disciplines. Studying coordination compounds offers insights into fundamental chemical principles and practical applications. Their unique properties make them essential in fields ranging from healthcare to environmental science. By mastering coordination chemistry, we gain tools to solve real-world problems and drive scientific progress. The world of coordination compounds is vast and ever-evolving. For those interested in exploring further, resources like textbooks, scientific journals, and online courses offer deeper dives into advanced topics. Whether you're a student, researcher, or enthusiast, there's always more to discover in coordination chemistry. In conclusion, coordination compounds are a fascinating and essential part of chemistry. Their unique structures, diverse properties, and wide-ranging applications make them a subject worth studying and appreciating. As research continues, coordination chemistry will undoubtedly lead to new discoveries and innovations that benefit society and the world.